All right, now here we are looking at the bijection rule again, what you read about in the Zybook. Now in the Zybook they call it a definition, and I don't like that. That bothers me. I don't think that the bijection rule for finite sets is a definition. It's actually a theorem. It's something that we can prove. And so let me show you this isn't a rigorous proof, okay? This is not a rigorous proof, but this shows you why it's true. And I think from the previous example with the hands, it helps you to see why it's true. Okay, it's going to be important later that we think of this as something that has been proved. This is something that we know is true, not because we say it's true by definition, but because we know it's true because we proved it. Okay. All right, so to prove something like this, where we have this double arrow there, that's the same as if and only if. So basically what that means is that if you know that's true, then you know that's true immediately, and vice versa. If you know there's a bijection, then you know that they have the same number of elements. If they have the same number of elements, then you know there's a bijection. All right, so there's two things you got to prove. So to prove an if and only if statement, you assume that, show that. Then the next thing is assuming that and showing that. Okay, so let's assume, let's make this assumption, and we'll show this right here. All right, now this is a very visual proof. Don't get too freaked out. This is basically what we just said before. Okay, look, right? If A has this many elements, whatever it is, and B has this, we're assuming that they have the same number of elements, right? So in this case, it's 5. Right, this is why it's not rigorous, because I'm actually using the number 5 and not n or something. But you know, that's not the point. Okay, look. This guy has 5 elements. I put them there. So this is A, this is B, right? As we saw before, we can put those together in the same table with the count column down the center. Why even worry about the count column? We can just eliminate it and get a bijection. How do we know that's a bijection? Well, let's just check again real fast. Let's see. Well, these are all different. There's no D and E's, and these are all different. Okay, so that's a bijection. Right, so let's just see real fast what we proved. Right, our assumption was that A and B had the same number of elements. That was this and this here. And then we can put those together very simply just by lining up the count columns. Why even worry about a count column? Just put them together. Look, they line up. There's a bijection. That's it. Okay, now for the other direction. We assume that if there's a bijection, then things have the same number of elements. All right, so let's start here at the top. All right, we'll assume that there's a bijection from A to B. Okay, here's our bijection. How do we know it's a bijection? All these are different. There's no D and E's, and all of these are different. Okay, that's a bijection. Okay, well, we could put a little count column right down the center if we wanted to, right? I mean, it's not changing the relationship that A is related to alpha, B is related to beta, C is related to triangle, and D is related to lambda, and E is related to rho, right? I mean, oh man, I noticed a mistake. This thing got messed up there. That should be a triangle. Okay, well, I guess that's the only mistake. So I'm just going to go with it, because I don't want to remake this thing. Okay, so that's a triangle there, okay? Everybody, you gonna be okay? That is a triangle. Let's see how many times I can draw a triangle. That is a triangle. Okay, all right, we got it. Okay, so starting over again, right? So you, assuming we have a bijection between A and B, all right, this is our assumption, right? That's assumption. That's our assumption, that we have a bijection between A and B. We can insert a count column right down the center, no big deal. Then we can split things off, right? We have how many elements does A have? A has however many the count is. How many does B have? B has however many the count is. Okay? So then they have the same number of elements. Who cares that it was 5? I never actually used the fact that 5 was 5. I don't know if you noticed that. Right. Okay. All right, so that proves the bijection rule for, let me just go back up here real fast. That proves the bijection rule for finite sets. And that's really that's what I aim to do, is to show you that this is true, not because we say it is, but because we can prove it to be true. Right? This is truth. Right? You can see that it's true. True.